Okay. Yeah, so the recording has started. So last time we discussed about the agents and the way the agents can perceive and then perform actions. And we saw an example of a vacuum cleaner robot. And we said that, okay, the vacuum cleaner agent can, if the task of that agent is to clean the room, then, and if there are two rooms, A and B, then you can try to solve this problem by simply developing a rule base. And that rule base will take input as perceptions. And then those perceptions could then be translated into actions based upon whatever has been perceived. And let's say the perceptions would include that the robot would know, would try to identify in which room that robot is, A or B, and then would also try to identify whether that room is dirty or not. Okay. And that can actually be written, or that can actually be seen as, say, two percepts or perceptions that are made about the environment and the presence of that particular robot. So here it says A, dirty. This means that okay. So Tariq, you can share the Zoom link with them and they can actually join in. Or you want me to wait for them to join in? Whatever you say. Okay. So that's the perception that one can actually have, or this particular vacuum cleaner robot can have about the environment and about itself. And then the actions could be associated with whatever has been perceived. For example, the movement action would be that the robot could move left or right, and then the robot could actually suck in the dirt or clean the room. And if both the rooms are clean, then the robot could actually just sit in a room stationary with no operations being carried out. Okay, so this is what we saw last time, that you can actually have a small reflex vacuum agent. Okay, just a minute. Let me just see if there are. Okay, so you can actually implement this type of an agent using a very standard, simple lookup table. And that is what we have here. We have got a very simple lookup table. So what happens is that you actually perceive a certain sequence, identify that sequence, and then based upon that, you take some action. And that is what this is how an agent could actually work. Okay, so we we also had a look at various conditions in the vacuum world where a robot could actually be in a single state, deterministic state. That means that it's able to identify that in which state out of these 8 possible states the robot is in. If that's obviously the case, then it's the first scenario, which is primarily a single state scenario. The second possibility is that the robot and the environment is sensorless, and say at least one sensor, which is the location sensor, that is an identification that whether the room is dirty or not is not working or is not there, then that would be a non-observable state or sensorless state. So in a sensorless state, the robot could actually be in any of these 8 possible states. And how would the problem be solved? That problem would be solved by assuming that the robot is present in any one of these 8 states. So the robot could start assuming that it's in states 3, and then let's say start operations based upon 3. And that is the case in case of non-observable or sensorless scenarios. So then it's basically robot is unable to basically identify or perceive the environment as well as its own location. Therefore, it can assume to be in any state and then start its operation. And of course, there would be some redundancy in this case. There would be certain conditions under which, there would be some sort of actions that will be taken that are repeated or that are probably not required. Say, for example, if the robot is in state, assumes itself to be in state 3, but actually the actual state was 5. So cleaning room A won't make any sense, because in 5, which is the actual situation, room A is already cleaned. But because the robot is thinking it's in state 3, it would start cleaning room A as well. So this is what, so one is perception and the other one is reality. So in reality, the robot could be in 3, but the perception that the robot is having because of this non-observability or because of the sensorless condition could think that it's in state 3. Okay. And that is actually a problem when you have a sensorless situation. Okay, so we discussed this last time. So what you can do is that when you are trying to solve this type of a problem, or when a computer is trying to solve this type of a problem, these 8 possible states can be connected together. And these states are connected together through a representation, through a method which is shown on this slide, which we call as a state space representation. So this is actually a state space representation. When we say state space, all these states, these 8 possible states, are actually connected together, and they are connected together through a representation which is called a tree representation or a graph representation, depending upon some conditionality. And we'll talk about these conditions later on. Okay. So this is a state space representation of all those 8 states that we discussed in the previous slide. So if the robot is, let's say, in this state, is present here, okay, then the robot could actually move to the state on the left, or it could move to the state on the right, okay, in this particular fashion. And there could be other transitions also that could actually be made, okay. So this type of a representation is a very important representation, which we call as a state space representation. So whenever, and in order to solve, so what will be the problem that you will be solving in this case. So first of all, you will try to, the robot would try to identify in which state that robot is. And then the goal state is obviously to clean all the rooms and then probably rest in room B, which is this state. So that's our goal state. That is what you want to achieve. And let's say you are actually present, the robot. When I say you, it actually means the robot. So probably let's say that the start state is here. So this is what we call as the start state. This is what we call as a goal state. That is the ultimate goal that you want to achieve. You want to clean both the rooms and you want to actually then rest in room B. And this is the present state in which the robot is in, right? Now the task here will be to find a path that connects your start state to your goal state. So you need to find out a path. And when I say a path, it actually means that you need to find out the sequence of actions that are required in order to move from your start state to your goal state, right? So that sequence of action is to be determined, right? And that sequence of action has to be determined. And that can be determined using this state space representation, which I have actually given you. So what would be that sequence of actions that you might take in order to reach your goal state if your start state is this? Okay, so let me give you one, and then you can think of many other ways of reaching your goal state. So the one possibility of moving from your start state to your goal state is that, okay, you can actually from here take this action, which is on, which takes you to this situation. Okay, from there you can actually go to this state, taking the action, whatever that action, required action is. Then from there you can actually go to the next state. From this next state you can actually move on to this state, and from here you can actually move to your goal state. So if I just redraw this, the sequence that you will be getting from your start state to your goal state would be that, okay, so this would be this. So you go from this state to this state, then you go to the next state. From here you can move to the third state or the fourth state, to the fifth state, and then to the final state. So this is like one path, the sequence of action. So what is the first action that you take? You move to the right. Okay. Then the next action is that you suck the dirt. The next action is that you move to the left room. Okay. Followed by is a cleaning room, which is on the left, which is room number A, which is this state, and then finally moving to room B and rest at this particular state. So this path that connects your S to your G is shown here. So this is just one possible path, right? So this is one possible sequence that you can actually get. There could be many other sequences that you can get from this state space representation. So why do we have this state space representation at the first place? The reason that we have this state space representation at the first place is that we can actually get a sequence, and we can develop, because of this representation, we can actually develop an algorithm, a solution. Okay, so we can develop an algorithm, or we can determine the sequence of steps that can actually be required. So an algorithm can actually be developed, which could actually connect my start state to my goal state. Okay, which can find out that sequence, right? Okay, so let me ask you a question. Can you determine, using this state space which is given here, can you determine any other path that connects your start state and your goal state. I mean, the sequence of actions that would take you from your goal state to your, take you from your start state to your goal state. I've given you one. Can you identify any other path? I mean, you can write in the chat if you want, or you can open up your mic and talk about.
Please.
Yeah.
Execute. So I guess we can start from the first state at the beginning, where the vacuum cleaner is on position A or in room A.
Mhm.
Then it goes down to the left, where it
Okay.
cleans position A.
Mhm.
After that, it moves to B,
Okay. Right. Moves to the right.
and then it cleans B.
Yeah. Okay.
And this is our goal.
And that is our goal. That's excellent. So okay. So this is like another path. So I gave you one path, and you have given me another path. Similarly, you can actually have multiple other paths. Okay, so how would you compare the two paths? So let's say my path, which I have given you earlier, which I can actually, let's say, represent by the red color here. So let's say this was probably the path that I gave you. Okay. And your paths, which you have just mentioned, I can actually represent that with this blue color. Okay. So yeah, so I can actually represent this with this particular. So these are the two paths. So if I ask you to compare the two paths, right? So how would you compare these two?
The path in red, I guess, feels less convenient than the blue one, because at the beginning the vacuum cleaner was at position A, and it was dirty. So it's more convenient to clean it and move to position B, because at the end the vacuum cleaner has to stop at position B, and that's how where our goal is. No, in the red path, it took more steps to reach the goal, 6 steps, and the blue one was only 4 steps. So it's like,
Yeah.
uh,
You are right. You are right. You are absolutely right.
the word.
Yeah. So the red path seems to be a longer path, and then there seems to be some actions that are really not required. I mean, why would you move from room A to room B without cleaning? If you know that room A is not clean, so you should first clean it and then move. So if you compare the blue path with the red path, you can very easily see that out of these paths, you have to choose, one should choose the best path that is available. Okay, and that is one of the purposes of using AI here, or some algorithms or some methods that can actually return you, or that can actually give you the best possible path. Okay, and that path identification, as I told you, the first step that is required in identifying that particular path is to represent your problem in a manner that you can use computers or algorithms or programming languages to implement the solution strategy or the solution method in a program. And why do you require a program? The reason for that is that you can actually implement it in a computer. In order to implement something in a computer, you have to program it, or write an algorithm in some programming language. Say, for example, Python or some other programming language. Okay, so one of the purposes of using AI and the methods that we'll be studying is to give you the best possible solution. So if you have got alternate paths here from moving from one place to another place, Okay, so you can have alternate paths here. So you can have another path here, for example, right? So one of the purpose of using AI is that you should actually come up with the best possible path, and the best possible path could be dependent upon various things. For example, here we can say that, okay, the number of states that are between your start state and your goal state, they should be as less as possible. That could be like one way of defining the best path. The other could be that, okay, you define some cost factor. Say, for example, every time you perform an operation, say, for example, you move from one place to another place, from one room to another room, and then you come back, every action you take incurs or has some cost associated with it, right? So the other way of defining could be in terms of cost. So you can say that, okay, one should select a path that gives me the lowest cost. Okay, so in other words, the number of operations that are required should be low. Okay, so that's another way of looking at it. So, I mean, you can relate this to navigation problem. Also, you are moving from, you are in a country and you're moving from one city to another city, and there are multiple routes that are available. You have got a map in front of you, and there are alternate paths that take you from one city to another city. Okay, so you can ask yourself saying that, okay, I want a path that gives me that actually incurs the least fuel cost. Okay, it should be less costly. So, and in order to solve this problem, what you do is that you take that map, digitize it, put it in a computer, represent that map in the form of a state space, very similar to the one which I'm showing you on this slide, where states could be, say, junctions, or let's say road connections, or any landmarks which are present in the city. And then the links that we have here, they could be the roads or the streets that are present there. And now if you want to solve this problem, the first thing obviously would be to actually represent it in the form of a state space representation, which could be again a graph representation or a tree representation of this form, of this form, which I'm just writing on the slide here on the top left corner. And then using this state space representation, you can apply algorithms that can return you the best path. And again, you will have to define what best means. Okay, so it's in your control that how would you define what best is. Okay, it could be in terms of cost, it could be in terms of time, it could be in terms of the number of nodes or the number of states that are present in between. And at the end of the day, for some problems, most of those things mean one and the same thing. There's only a way of expressing it differently. If I say that the cost should be low, then that would in other ways mean that the number of actions that the robot is taking, they should also be low, because otherwise the cost would increase, right? Okay. So you have to be a little careful in this, in defining this. So this is what the problem solving strategy in AI would be. And I'll, at the end of today's lecture, I'll give you the complete AI pipeline that how a particular problem which is given to you, how can you actually solve it? What are those steps that are actually required? Okay, I hope this is clear, and we can move on to the next point. Okay, so let me just move on to the next bit. So before that, let me just clear this all. If I can erase these things. Okay, so here is a small video. So this and I'll just show you this video. This is actually solving another type of problem. And this problem is related to, okay, so if I can play this video here, I think, let me just see if I can play this video. Yeah, so let me just see that what this video is all about. Okay, so this video is about okay. So this is called LipNet. So what are you trying to do here? She's speaking something and you're trying to read the lips. Okay, so you from lip reading, you're
Like
trying.
when I'm one saying.
Yeah, you're trying to identify what she's trying to talk. I hope you can see this.
Play red in X-ray zone.
Set green with U zero again.
Okay, so this was actually a small representation of another AI agent, which is called a LipNet. And what is this LipNet is doing? You have actually seen that in the video, and that this LipNet is trying to read what a person is trying to speak. And it's said in the video that a person who is a lip reader is the efficiency or the accuracy of that person is around 52-53%, whereas this lip reader accuracy is around, let's say, 93% or above 90%. Okay, so if you want to design, so the vacuum cleaner problem we discussed, a problem that was altogether different. Here we have a problem which is altogether different. I mean, for here, the definition of the actuators, the definition of the sensors, the definition of an agent function, the environment of the problem is completely different now, right? And you can again, but the problem solving strategy would remain the same. So what would be that problem solving strategy? The problem solving strategy could be the methods you are trying to solve is the problem which you are trying to solve is that here you want to see the movement of the lips, and from there you are trying to identify, you are trying to find out that what that person is trying to speak. Okay. So the problem solving method, you can again employ a state space representation in this case. Okay. The definition of the state will become different in this case. Okay. And the transition from one state to another state would also be different. And what would be that state space representation? So let's say if I want to develop a state space representation for this LipNet problem, what comes to your mind? I mean, what do you think? That what type of a state space can you develop? What would be a state in this case? What would be the transition from one state to another state? What would that link mean? Okay. So can anyone suggest something?
Excuse me?
Yeah.
I think that there must be data predefined into how the letters are pronounced in English, how the mouth seams with each letter, and the connections between them is how the letters are connected. I don't know if it's right.
Yeah, you're right, mostly. So you need to first know that how a letter is actually pronounced. So what is the movement of how the lips actually move if you want to pronounce some letter. Okay, for example, if you are pronouncing A, B, or C. Okay, so you need to know that how the movement actually takes place. Okay, and then and every say, for example, position would represent, every position would represent a state. Okay, and then the transition from one state to another state would primarily represent the transition from one alphabet to the second alphabet. Okay, but there is a problem here, and that problem is that are we talking about alphabets here or words here? Because alphabets connect together and they form words. So do you or would you be able to identify the alphabet level movement? Or would you be more comfortable in identifying say the movement of, let's say, a group of alphabets? So if A followed by I comes in, so if you want to, let's say, pronounce air, then how would you go about? Would you try to identify A, I, and R separately? Or would you collectively see that if a word air is pronounced, what is the complete movement of the lips? So which one would be easier and which one would be more difficult? Or which one would be more challenging out of these two? Word level recognition, or let's say alphabet level recognition? So what's your take on this?
Alphabet level recognition will be easier because every word is divided into alphabets at the end.
Okay. So anyone who would like to challenge this or who would think otherwise? Is there anyone who would actually suggest no, word level recognition would be relatively easier compared to alphabet level? Maybe Osama, if you can, if there is a difficulty in, let's say, understanding the question, you might assist us.
I confirm with Rania that we can partial our problem if we say the word is the problem, and we can solve it when we know each character sequentially.
Mhm.
So, and beside that, we have a dictionary or something like that. So we will know the statement, what it's mean, or
Yeah. Okay. So what Rania said, I also agree with her, but there is one problem with that. And that problem is that segmenting alphabet level, say, movement would require, say, relatively very slow movement of the lips, or you'll have to play that video very slowly so that you can easily segment that out. Whereas if you are trying to recognize a complete word, in that case, the segmentation would be, or division of these, or the collection of movements would be larger in number. So you'll actually be looking at the sequence AINR, air in case of air, that for air or word level recognition would may require a relatively faster, let's say, play of the video. So that is something that is still debatable. I mean, there is no one unique answer to this, but anyways, yes, go ahead.
I want to say that if our data set, the predefined data, depends on words, then the results we get will be faster because we recognize a whole word, not and we don't have to divide it into its letters. But this will, I guess, this depends on bigger efforts in predefining the data set.
Yeah, because the number of alphabets that you have are less, but the words that you get finding these alphabets together, that set is much larger.
العصفور السوري لا ما يجي الحرب ثالث شهر واحنا عند رصيد عاق وضل في البدروم حطيت له اكل ميه على اساس انه يكفي
So is it?
طلعنا عرب
So shall
ضرب
I?
ودار لخص من هنا القفص كان في نص البدروم
Okay.
فلاقي لك القفص
Right. So that's actually a problem, and that again depends that what strategy would you apply in order to solve this type of a problem. So for word level, you'll have to have a larger data set, of course. But then it would depend upon person to person also. Like, so you may have different people talking at different speeds. The way you pronounce those words also change, and that is in every language. I mean, there is an accent difference also. There are other issues also. But anyway, this is a complex problem, and the agent function that you will have to define in this particular scenario, the agent function, that what type of problem would you try to, or what would be the strategy of solving this type of a problem? Would it be a state space representation, and then you find out the sequence and identify that what is the end result? So that agent function that you need to define for this problem would also change. I mean, state space representation or the search oriented problem solving method would be one. There are other ways of doing it. But anyway, it's a complex problem. Okay, so let's try to see another problem that one can try to solve and see the level of complexity that is there in that problem. So let me just move on to the next application. And this application is was developed in MIT. This is what we call as a mini cheetah. If you just run this, I'll just run it and play it, and you can have a look at it. Right. So this is another application. And again, you can see that the solution strategy or the method through which you can actually solve this type of problem could be the same that you apply for vacuum cleaner or for the lip net. Here again, the agent function, and the agent function is not just performing one task here. The agent function is performing multiple tasks in this particular application, this mini cheetah application. And those tasks are obviously one is related to the movement, the other one is related to recognition. So that robot is also identifying that ball is coming, is also towards the robot, is also trying to estimate the distance of that ball, and then it's also coordinating its jumps based upon the input that one is getting, or the robot is actually getting from the environment. Okay. And these are like some of the tasks that the robot is actually trying to perform. And you can see that obviously sensors that were incorporated in this particular type of a robot, they included vision sensors, for example, must have got a camera there. Then maybe say for distance estimation, some sort of sensors would be employed in this particular scenario again to identify the distance. A software agent that would identify or recognize objects, for example, identifying the football is like one of the tasks that this agent is trying to perform. So you can see that it's altogether a very complex sort of an agent, right? And has got some very sophisticated sensors, and then the actuators, which are actually performing the actions. For example, for jumping, there would be some obviously movement. For movement, some motors would be employed. Those motors would make the robot move, jump, and then turn. So all these are the different types of agents, the different types of sensors, and what action should that agent or that robot be taking. Again, that problem solving can be represented in the form of what? In the form of a state space representation also. So if you see a ball coming towards you, this is a sequence of action that you need to take. Okay. And again, this can be represented in the form of a state space representation and can be solved as a search problem or as a problem which finds the path between your present state and your goal state. Right. So any questions about the discussion that we had so far? If there are any questions, you can use the chat box also, or you can use your mic also to ask any questions if there are any questions.